Hello everybody, I want to introduce you guys to chapter 8 with this section 8.1 notes, which the title is Distribution of the Sample Mean. So we've seen before, having a distribution and being able to calculate the mean of that distribution. For example, we've seen normal distributions, we've seen binomial distributions, and this one is going to be actually pretty interesting. It's an interesting idea what we're talking about here. It's the distribution of the sample mean. So the idea, if you can form this idea in your head, what we're thinking about is that there's a population and you can take means, of you can have a mean of the population. Of course, the population will have a mean, and that's the one that we call, of course, the population mean is the symbol mu. But imagine you take a sample from the population and then you calculate the mean of the sample. You might get the same thing or you might get something different. For example, if we have a class with 20 people in the class, so for this particular class, n is 20, and then maybe we're going to take, should be the big N though, because it's the whole class has size of 20. But then what if we're going to take little samples from the class of size 4, and we're going to talk about maybe your average, the class average on the test grade. The class is going to have a particular average, but if you take a sample of size 4, and you find the average for just those 4 students, the average might be above the class average, it might be below the class average, or it might be the same. But what's very important to notice about this one is that in a population of 20 people, say this is a class of 20, and you take a sample of 4 students, there's actually a lot of different samples that you can take. And I want to ask you, how many samples could you take of 4 students from a class of 20 students? Can you imagine whether the order would matter? Because then here we're talking about whether this is going to be a permutation or a combination. Well, of course, if you have the same 4 students, it doesn't matter which order you selected them. It would be the same sample of 4 students. So in this case, the order does not matter. That means it's a combination. So how many combinations do we have that we can take of 4 students out of a class of 20? Let's go to the combinations there. It's number 3 out of a class of 20. How many combinations of size 4? So in a class only of 20 people is kind of amazing. You can take almost 5,000 different samples of size 4, and that's even if the order does not matter. So once you have, and that's actually something that's pretty nice as well, this class only has 20 people in it, so that's a pretty small population. But now if we're considering all of the different samples, now there's almost 5,000 samples that we're considering. So if you make a distribution of these samples and what their mean is for each sample, then we will end up actually with 4,845 different data points to plot, instead of having, for example, maybe you just take the 4 students and plot their data, or else even in the population of 20, that's just 20 data points that you would plot, their scores on the test that we're talking about, the average. You can plot 20 test scores, or if you take all the different samples, you consider every sample of size 4, then now you have almost 5,000 data points. So it's an incredible increase. But in general, all of that to say, we're talking about a sampling distribution, which is when you consider all of the different kinds of samples that you could actually take, and then you plot for a given statistic. So you can be talking about any kind of statistic like mean or standard deviation or whatever. Just choose your favorite statistic. A lot of times, at least what we're talking about at the beginning, is the sampling distribution of the sample mean. And so this is a case where we're going to talk about, if you have a population with a certain mean, then what should be the mean of the sampling distribution of the sample mean, where we have take all these sample means. I think, to be honest, it would become more clear by doing an example. And we are going to, for our purposes, we're taking these samples with replacement, just so that the events are independent. We don't have to worry about the probabilities changing and so forth based on who we pick. So here in this example, we're talking about these 3 people. So it's a very small population, only 3 people. And what we're going to do is, notice this is supposedly their net worth or whatever in billions. And Warren Buffett, it kind of wraps around. He goes with the 61. So what we're coming up here is, first we're going to list all of the possible samples that you can take. And since we're using replacement, it's possible to pick the same person twice. So this sample this sample with the 75s twice, we happen to pick Bill Gates twice. But what we have here, these are actually all the samples that are possible. We can get both 75, or we can get 75 and then 67, or 75 and 61. These are all of the combinations of length 2 that you can get out of a set of 3 things. And so we've just enumerated them here. And then for each of these samples, we calculated what is the mean of that sample. So when you get both 75, the average of those two is, of course, 75. And what we came up here with is that there are 9 different possible samples. That should be actually what we get by finding the number of combinations of size 2 out of a list of 3 people. And I just feel like looking at it out of curiosity. No, this cannot be correct. Why? These are... Oh, I see. It's because we're able to pick them twice. It's because we're using replacements, so this is something else. This would be actually just the multiplication, because there's 3 possible things in the first pick, and then there's 3 possible choices for the second pick. So there's 9 total possibilities. And then we're going to see that for each one of these sample means, there's basically a 1 out of 9 chance to pick that sample, and so there's a 1 out of 9 chance to get that mean. But notice some of them repeat themselves. We got 64 a couple of times, we got 68 a couple of times. And so what we're going to look at, out of all these different sample means that are possible, these were the different means that we calculated. What is the probability to get this mean? So for 61, that only happens once. So that's basically a 1 out of 9 chance. And then what about for 64? Happens once and then twice. So there's a 2 out of 9 chance to get 64. And then for 67, looks like only once again, right? So another 1 out of 9. Now we're looking at for 68. Happens twice. Once, twice. So 2 out of 9 chance for 68. And then what about for 71? Happens also twice. 2 out of 9 chance. And then last but not least, 75. Happens only once. 1 out of 9 chance. And so we can plot this one if we wanted to. We can say, maybe a histogram or something. This one can be 61, and we really don't need, this is going to be a pretty basic looking graph. 61 can go up to here, and then maybe 64, 67, 68, 71, 75. I hope they will fit if I was counting correctly. And then we can just make kind of a histogram out of this one. And I'm sure that yours that you're making, if you're following along with this one, looks a lot better than mine. But I'm just carrying on and making some difficult pen strokes. And this one goes basically 1 out of 29 chance, or 1 out of 9 chance rather. And the highest that was even possible is 2 out of 9. And then we can make our little boxes. So it went basically 1, and then here we'll have another one, and then went like this, And so this is a pretty unfortunate looking histogram. Oh wait, what am I trying to do with this one? That's also a 2 out of 9 chance for 71. And then 1 out of 9 for the last one. And so this histogram, it's not a very visually appealing one. It's kind of bimodal or uniform or something. Maybe you call it uniform shape. It's definitely not bell shape because it wants to be bell shape, I can tell you that. But it's not. Bell shape is just what we desire from anything. We want it to be normally distributed, will be a bell shape. The fact is that here our population is very small, only 3, and our samples are small, having only 2. And what we will see is that and actually what we've drawn here, this histogram, the very ugly histogram that I drew, is the sampling distribution of the mean. We just drew one. This is our first ever sampling distribution of a mean that we've seen. It's this thing over here. And the idea is that as the sample size increases, which is, the population has to be bigger for this one to increase. As the sample size increases, so the little n, as that gets bigger and bigger, we will approach more of a bell shape. And consider this distribution. Is it bell shaped? We're asking ourselves, is this one bell shaped? It's up to you to say whether it's bell shaped or not. It's kind of meh. It's a little bit of an opinion at this point because this is a funny example. But anyways, we want to calculate the mean and standard deviation of the sampling distribution. So here, how would you calculate the mean of this thing? That is a question. It seems appropriate to calculate this mean by thinking of a weighted mean, if you can remember this one, the weighted mean. And to calculate the weighted mean, I kind of feel like using the lists, because lists are our friend. And I have all of this old data from previous times, getting rid of it. So we can go into here with our first bit of stuff. I'm going in here with the means into list 1. And then once I have those, oh no, what happened? It goes 68, and then 71, and then 75. Those are our 6 different means, and then we have 1 out of 9 for this one, 2 out of 9, 1 out of 9 again, and then 2 out of 9 twice. And I believe that our calculator will assist us, now that we have our list made, to go into stat, calc. Really, we're doing one of our stats, because we have a frequency list this time, and the frequency list is list 2. So what happens when we calculate it? The mean is, it's this one, the 67.6 repeating. So I'm going to put that one in there. 67.6, and then it just repeats somehow. And what about the standard deviation? It gave us that one as well. It's this kind of 4.05, or maybe 4.06. That's good enough. So we found the mean and standard deviation of the sampling distribution thanks to our graphing calculator. And now what we're interested in is this question of, well, what were these values for the population? Because all the time we're dealing with this problem in statistics. You have a population, but the actual parameters, like the mean and the standard deviation of the population, it's something that we don't know, and we're trying to find it out. If only we could approximate it somehow, or try to guess or something. That's what we're dealing with in statistics. Try to figure out what is the mean or the standard deviation of the population based on a sample. Well, here we're in the business of doing that, and we found the sample mean we found the mean for the sampling distribution. We found the standard deviation for the sampling distribution. And that's the question, how do they compare to the real one? And so that's what we're wanting to do here, calculate the mean and standard deviation of the population. Well, if you can remember, the population values were just 75, 67, you can't circle that one, and then 61. 75, and so why don't we do it? I'm going to go this time into list 3 with those values. It was the 175, 67, and 61. And now, oh wait, did it take that value? It did. So now I'm going to go to stat and calc. This time I want to use list 3. I want to get rid of that one. And what do we have? It's good news for this one. The mean is the same as the one that we just found. It's 67.6 and then repeating. The standard deviation, it's a little bit different. And of course we want to use the population one, the one that goes 5.7. We will see, actually, maybe I'll give you guys a little bit of a spoiler, is that there's a definite way to find the standard deviation of the population using the one from the sampling distribution of the mean. But we finished this example for now, and then we're going to carry on with some of these, and of course here are the formulas there for your viewing pleasure, but we will carry on here in a little bit.